all. Thank you for the presentation. This series of talks. I can say something about this John it shows you about all this thing that some of you have already heard about. Some maybe this year, which is this thing called analytic. So maybe let me start with basically the goal of all the vector. Okay. The goal is maybe to motivate why such a kind of object should somehow exist. Why this sort of maybe there are at least there are two kind of source motivations. One is more like maybe evidence measure point from evidence, and the second one measure point from something like you. Yes. And so the goal is to yes, how we can believe that exists and why it's not the time. Yes. And also explain that construction that in some cases maybe still construction in progress. So maybe the first motivation again is like a proof of that comes from value theory as a solution. And well, similar to what happens with prismatic cohomology with schemes, we would like to have a nice cohomology theory for which you can relate different phenomena from other value theories. So in the case of analytic geometry, we have a theory that may look similar to those from value schemes, but still that has different kind of values. So let me start with maybe mechanism of them. One data will be back together. Analytic. Example, which are kind of it could be like real spaces. Or maybe something like analytic spaces. Objects that look like something actually analytic. Examples of cohomologies, I think that maybe we're already studying a lot in years, people. The first one is the Prometheus cohomology. And cubic coefficients, maybe some local system, some space. And these ones are related with the metallic cohomology proper schemes. This is the proper case, as long as your local system has some kind of nice intermodals. But again, here shown us that these are not the only interest ones. So maybe put an example of something weird that like zero. So take one over speed. For size. just see. And take this Drinfeld space. In level, CP is going to be 0 to a few meters. Diamonds, and from this you can hook up protocol chip. No, just by taking the standard representation of CO2 and just descend it along this torso. This one you can see, but this one doesn't come from the problem. Yeah, we already encountered objects that just exist in this, let's say, more analytic world. And, well, let's say, we also know the different means that the cohomologies of this protocol chip, even though we start using proper smooth variety, are no longer five-dimensional cubic vector spaces. These are given by fancy that are these Banach spaces. On the other hand, in character theory, it's much theory and much theory involve dimension. We also want to relate one ordinal the adding. Maybe the kind of differential operators that we like to see there are not just the right ones in the analysis. Similar to what happened for a complex equation that take a complex variety, maybe a real manifold, and you look at the algebra of endomorphism of the sheaf of the reals, you end up with this sheaf that is called the sheaf of infinite order of differential operators. Here you have something analog. Right, just the cohomology and not
Then
right. So as if you have a let's say proper smooth right.
and then
random regenerative space with no so once in the perfect space. So your space is proper, not by the subset. It's like converting and if you have a nice inflow model, it's just going to be the simplified model. So take what's different from right. So now you have a take this. Things like product cohomology are very, let's say, almost like they take place maybe not the one there. So you can kind of solve this by working with all project theory steps. Yes. Yes. This at least what experience with the stars is if the correct answer will be the analog for having working then not. Yes, I think you will get even some huge non-constrained spaces, maybe these very good spaces, and this is because you end up with this cohomology using some really curious some infer construction, some big vector construction. It's not that it's incorrect, it's that you're seeing a different phenomenon than in the lab. Now, there's some the same answer. It's not that it's correct, it's that it's not going to give the same answer as the body. So it's going to be may not be quite correct. Yes. And I think it's not low. Yes. No, I what is going to happen. All these look at people even success, but actually not. It's not that get different features. So yes. So, maybe as pretty spaces, we have yes, yes, we have see like instrumental, incremental space, not helpful property spaces, and then there is shape, but which one is that? Sorry, yes. Yes, it is. It's just reflections underlying. And then you can define it. So by constraint model. Cohomology of the imprecise matter. But then similar, okay, like prismatic homology, right? Prismatic homology that exists that this stack or constant stack, which encodes more geometry than somehow we chose at this point. Particular stacks could be related with some twisted version of the right? Or like symmetry. Which is something that we don't see here. Still, the quality should be the same as this one. So, in the case of constraint logic, it's very happy with this one. So, yeah, the thing. And sample this. What is homology is so this completion of the verb. This homology homology justice. What does it say? Yes. Still, again, like motivated prismatic cohomology value for schemes come from this work of Bhatt myself, geometrization theory. Let's say there should be a alignment of this hot state cohomology to something that should look like, again, so analytic hot state. Essentially, this is just showing that this cohomology should be able to compute this. There's some experience. Yeah, this that's what it is. In the sense that this commodity should coincide with the commodity of substance. Yes, yes. So this, we'll talk more about that in the seminar on the number books. Yes. This type of similar or analog.
like this description of so I mean this description of the cohomology. I mean it's also giving a also I mean it's also giving you a stack maybe that should be like the check number of nothing or like something, but like it's a refinement in particular. It's more refined with that.
It's more refined. Yes. This gives you for you something that I have takes, which is just one start because of going some component is theory. And this one is, as I should say, as well, this level of any background. And what we want, because again, we want something related to the differential operators. How what we find this looks continuous. Okay. Means that continuous function. That's yeah. Yes. Yes. So okay, we try to
So that's the point. That's the point. Yeah. Steps. Steps.
right. Yes.
And from that sharpness. Just yes. I was the difference X. Right. So
Still, this starts from point of theory. The theory is nice spaces. Spaces. Is locally, it's write it down as an explicit function. As a compute acting on an honest. Yes. It's and just how the space time, but it's particular space is free, but that what becomes to them. Yes, because now you're taking like the continuous functions of gamma, and you see this as a
so para
Yes, or at least really class of functions. Yes. Set of yes. So, but for this one, I wrote some expressions, which I think were some of this. There was some, yes, you know, that's space, that's space, so that this. It means that the description is not purely what the ring structure is, but at least the group is. Right. Yes. Functions like functions, some local analytic functions, and this sort of yes. So let's say that maybe this is a I'm going to say something that at least motivates why this theory of kinetic constraint of here is similarly provided for kinetic form schemes. To extent is that you have this formal completion of the nodes, it's dual, and the other one is just SMP. Basically telling exactly what you say, like have a power series with regards to this 1.1, and it was scope algebra issues is the spaces with binomial issues. Yes, and at least I know of them, which are the important for us, which is this one on the local. The local analytic, what you get is basically the rigid version of it. Try to explain as much. Okay, so as a warm-up, let me package a very condensed way how to define prismatic cohomology in kinetic forms. Some picture. That will be at least a little bit motivating the way we're constructing this analytic conversation, and maybe all the other kind of related molecules. So I may start directly just talking about the prismatic side that keys. So for that, recall the basic definition. So the ring, then we have a notion of a data structure. And it consists of a map from the ring itself that is also called that derivation. And the derivation because will satisfy the following. So the local problem almost second song. That's nice. Nothing else. So what is also what we think about this appears well. We try to, let's say, somehow just reach the Frobenius and morphosis characteristic, key characteristics here. So let me give you an equivalent definition of the structure that maybe is more categorically quality. And what we first is a data structure. Okay. Second one is a refraction. Okay. Okay. But essentially, what you map is A to A to R. Okay. And the third one is what it is, just a Frobenius. But you need to be careful in which sense it appropriates. More anthropomorphism. Frobenius. Okay. Then reduce the Frobenius multiplication. And we take a multiplier, maybe the sense of the quasi units. Basically, it has yes. So fantastic. Then, thanks to this, the second definition, you have a nice categorical way to extend this to not just maybe rings, something like maybe just animate the bricks already. Let's just since all this theory of analytic geometry is very developed, this for animated rings, I'm going to just pretend that all my rings are that, even doing examples, not that common that the rings turns out to be still, just for the sake of I don't think that you're fully with me just for this. So I'm ready. Thanks. Okay. We also let bring a B, the food category of B. Then definition of a prism is a suitable kind of ideal, maybe suitable identifies on a delta ring satisfies the properties. So it should let A be delta ring. So prism on A is again identifiable. Maybe here I just done this in the possibilities. One is equal to such that it was two conditions. The first one is that A for any choice of any directional line is the analytic bit. And the second one, but again, it just happening in the underlying frame. The P is generated. It's the ideal directed behind. On the back. So there is a standard result in prismatic prisms. So arc. Well, maybe I should tell you what the morphism here is. So a morphism prisms. It's a map pairs. Say A to A, J to B. And it can go like that. And the quotients of rings. Basically, I'm just asking that these two have number of rings. Social. If these are just rings, then it's basically just a morphism of rings that sends this ideal to this ideal. But I also want this one preserve the structure directly. Then result in the classical theory of prismatic cohomology tells us that any such a kind of map of delta rings or prisms is already a push-out diagram. Arc if A to A, I to A, some of the prism, B, then this J is already just the base function. So not waste the following definition, will be standard notation. So let me take first maybe just let's say just the whole category of size to be simply contours from this total range. I know points in here. So it's just this again, kind of taking delta rings, and I just model out by some equivalence relation given by other delta rings, but again, maybe in a more mathematical sense. And let this one delta stacks, with stacks, to be map of the object that sends you a ring. And endowed this ring with the map extensions. Yep. Structure, just a line level and it's just a line. Don't solve that, that's enough. They can be on the I guess. Because this data is somehow the same as giving a map from this one to anyone. And then you just go put back the one there. Thanks. So far, it's just a novel. Remember the fact that it's a yes. Yes. Yes.
I mean, if you have a map of delta rings from A to A, you take delta rings, and I not extract on A.
Yes.
Like A prime not the ionic.
That could be true. Yes. But it's right. Well,
Sorry, the question was how to make it one of A.
yes, yes. Let me go. This is one question. I mean, you can solve this just by working over some other things. I mean, I need to the activities to this.
Suppose I want to extend
Yes.
should I
I think no, I think they're both. Let me say that this one is what I'm going to explain is a little bit of a mix of the prismatic side and the prismatization, like something that is essentially capturing the same say both of this I'm going to get the prismatic side and also both of this I'm going to get the prismatization.
Right. That's
Yes. Good one part of this.
second.
Yes.
That Fine.
Giving with that something. So I think the range will become here. So again, want to know the fact that this size will be incomplete, maybe not just turn the base. Maybe let me just forget that and just take the isomorphisms to be actual isomorphisms. Maps start this connection. So you could define the category prisms. We just a delta ring coming to this funny point. And it's just no, they're animated. Yeah. I just basically just for animate stuff to make definitions correct. But people think of them just to be nice. Yeah. So now there's another ring with some prisms. This is the definition of Bhatt-Scholze. Yeah.
It's more of a thing.
Yes.
Something
The animated story from the beginning. Yes. Also, when we say that there is this form of model, when it implies some animated version of what the properties are, and let's say treatments are, and also this is taking in the work of Bhatt-Lurie to study the absolute the relative second box. So also to take this one you can maybe delta rings and animated treatments. This one come from already somehow just a replacement of ideas of occurring in this. We got a point. That yeah, if you are prism, to just the brain. So now, again, starting on categorical way, write down what the prismatic side is. It's essentially always so. Length, just add steps, contours from 2 streaks. What the value stack is. And then we formally get contour that we may call geometrization from this category. Specs. Over this. And this will look a little bit weird, but essentially we're taking just another x and the market will be x such that we evaluate its replacement of k. We can So essentially, the prismatic side that is just the same as taking dot arrays and amalgam. We'll use the contours by push forward, which is just similar equations, which maybe fancy terms with the right chemistry. Yes. Essentially, our content categories, the take off, then shift by the contours, they just evaluate the image. Yes. Star is this one are contours, so no, it's right. Yes. This one is the right one. Yeah, it's zero fiction. Yes. I'm sorry, I'm so again, this is just a different way to see. It's not changing much. It's just something that looks like a bit more categorical. Just this site is essentially given by just this restriction function strategy. This stars just thank you to this function from this makes it. So now but next something. Yes. Yes. That's great. Yes. So this one is the input side. I was saying that this data of the prismatic side is essentially the same as making a delta ring which will give you with a delta ring with some fixed structure and just a point is a so now we'll look at the prismatization topics. So it turns out that you have another point from this delta ring. Okay. But basically just takes a ring with its delta structure and you just forget the delta structure. So this functor commutes with all the limits and co-limits. So it has a right joint. Given by the bit vector. So now, want to say define prismatic homology. So prismatic homology, Bhatt-Scholze, is defined as the homology of the sheaf defined by the data rings in the prismatic zone. So essentially, it's just the homology of the question sending to the understand this side don't like to be made. So this homology factors through this forgetting math. Basically, forget the function delta V computed. So instead of that, let us take some slightly more refined step before, and let us take just the underlying chaotic formal scheme, something here. So this induces map this was extension from these three stars. This one is an extension. Stars. It brings that essentially what you take is again just the sheaf co-represented by A with the data structure, and you map it to the formal sphere. You just forget the data structure and you extend everything by coordinates. So now, because you have this right adjoint, you can actually compute this F over streak very explicitly. So given an object is a delta stack, get that F over streak y evaluated in some point R is just y of the p vectors, natural vectors. And this is formally just from this to the junction you get at this step. Then it's just I'm just saying that you can compute this contour relatively explicitly using p vectors, just because you have this conjunction in them. Then consider the following diagram. So we start with a chaotic stack. We can then say it's essentially prismatic side here. One. And then we apply the contour. We're going to produce some chaotic style living over the F over streak of it. Then mission of inside. Then basically I want to consider this procedure. Some of these chaotic stacks in prismatization, not with that, going to be defined by. Let me just verify that this is actually prismatization. Fine. X what is it? Then G of X, this one is just the final object in this category. So not the final object. Yeah. So it's supposed to be a this one. Um, okay. Speak of it, yeah, it's given by the distance functions. Again, this is by definition what we call the prismatization. Arriving something given over the prismatization.
So also fine.
Yes.
And
Service.
so
First, the use of the cycle delta, which essentially corresponds to the prismatic cycle. And then I can forget the structure of the system and just end up with the prismatic. So again, this check like maybe R. Ring. And then evaluate this is R. R is just a map to the prismatization, which is just the normal thing. Both the same, and a Cartier device or the difference is prism. It's the same, just line is joint. You give it Cartier device to the practice of the
exercise one, you just describe. I forgot X. It's exercise one. I understand that it's must have been X.
Yes.
No, not that. I did not have a capital followed by X. Now this can be exercise one.
Sounds that. Right. So what maybe. And again, this one by construction, it just makes evaluated that part. Like, yeah, just now, which is the issue. Evaluate at this point. So yeah.
Well, sorry, I'm not sure if I understand this.
Do you mean like it's the same as R value?
But what I mean is that this is just a green with a map.
Yeah, so it's like an R value point of the card game. It's
Yes, yes, that's just.
So, example. Example one is.
Yes, yes. It was a clean edge of that. Yes.
Now, in what sense is that? So it's.
I mean, actually,
It's just a general.
sorry, I think that's example one may not be literally a because I mean it is, but not somehow for like for any you already need to know what is this map.
But then some answers what question.
Yeah, gives like this one is taking values in some free stacks of the proper street of one. Then I want to know over which.
So it's
Of this definition. Exactly. It's just. Yes.
And then I will actually.
Yes.
Now the fullness which is right. Yeah. Art is the.
These are
So it's.
So at least once you animate everything, prismatic cohomology would essentially coincide with the cohomology of this prismatization. Yeah. So when you side here. Right. Yes. So at the point where I presented the maybe non
So summary is right. So as far as I'm
yeah.
And so I can see that it's such
Maybe what I actually want to say is that you have this very nice prismatization concept. And well, this functor is going to factor to something else. This category of delta rings, which is a key like construction definition that plays an important role in prismatic homology. And maybe I'm not saying that this construction is better than this. I think both of them are actually important. Is that sometimes, at least for us, in what's going to be in the analytic prismatization, some statements will be easier to, like, I don't know, understand in this category than this. Even though this one. Right. Well, what is and a fun scheme. Right. That's short, right? Stuff. So let's say that one important feature of algebras that allows just basically the representation of the finite enough is that polynomial rings are basically generated by these algebras just kind of secret. This is not going to be longer true in the framework we're going to work. Still, you have generators, but these are not going to be compatible. It's not quite well, but it's abstract. So yes, it's not enough. Yeah, at least for schemes. Yes. I hope that something. Yes. And so again, this was like a very compact recall of how to be constructed prismatization and design more way. And I wanted to say something about the consciousness stack. How this analytic space stack was motivated by the work of Anschutz, Polygon, and Bhatt. But maybe before doing that, let me just broadly explain what is going to be the picture for us for this analytic prismatization. Not defining the objects, but at least writing down what is going to happen. Is going to be something. So analytic prismatization. Again, like as mentioned before, this category of rings where we're going to work is not, let's say, those doesn't have like these compact projective generators. In particular, this can be very easy because we want to do some kind of analytic geometry. And something we know about algebraic geometry that the affine line is compact and projective sense of category. Just take another line ring, filter polymates and with in other words, for example, the underlying scheme is just compact, quasi-compact. But this is not true for analytic geometry. The analytic affine line is no longer a quasi-compact space. In particular, you cannot expect like these category rings for which the underlying ring represented by this analytic affine line to be compactly generated. This one is already. So this is why we have a little bit more difficulty to try to define these maybe all categories just at the level of some kind of delta rings and just the little rings here. But something else that happens is that, let's say, the whole picture of the prismatization, this delta structure is going to be much more subtle. So usually for us, the delta structure was just a leaf of Frobenius in P-complete rings. It turns out that for this analytic prismatization, you don't want to talk with the P-complete rings because we want to see not P-complete homologies, such as the Rham cohomology or this product homology, different kind of homology. This involves that the notion of delta ring still should capture some kind of phenomena modulo P, but again in a more maybe analytic way. So it was a little bit of a trouble to try to find this condition. I think we already found it. And this involves some different and strange version of not just bit vector, basically about the both delta rings, but the over-convergent version of them. Kind of bit vectors with some broad conditions that encode somehow how the delta structure is. This makes the analytic investment more subtle than this one, but still, let's say at least over QP, we have this precise picture. Interval version, maybe we just have. So we want to define, first, we need to start with our geometry, right? So we need to start with whatever the reflection of this is going to be. So we want, let's say, the correct framework for geometry. And again, since we're going to see phenomena that is not P-complete and that makes look, for example, these locally analytic vectors, these different Banach or polynomial Banach versions of rings, we are kind of forced to already work on in the analytic geometry. Also because actually this sort of bit vectors here could be quite not separate. Not out. You actually need to keep track of this more refined content. And this one realized analytic geometry sense of Bhatt-Scholze and Scholze. And for that, well, we will need to introduce some new categories of rings that also play an important role in this definition of the analytic Rham stack. This use maybe some different categories depending on how we are. We just want to pick one of them. Something that we call by bounded rings. That essentially is just generalizations. make algebras. Since B space, I think that essentially can be written as co-limit of finite rings in a more, let's say, consistent way. Essentially, a co-limit of finite rings. That. And the other ones that category of these ones that well, basically is going to be the replacement for us. Maybe the best objects we have is like chaotic analytic geometry, which are these perfect spaces. We need something that still is not far from here, and basically we can recover any reasonable space, which is pretty space of them. But still, they have the nice features of perfect spaces. So this is something that we are going to call some new properties. Morally speaking, these are some kind of important elements. Perfect spaces. You can say a bit more further than that, but it's not part of the technical. So let me call these rings. Just being nice. I don't want to presentation job. And once we have these rings, maybe 0. Could be both of them depending what you do. And for the prismatization, maybe better the second ones. Good question. CP over bracket T. You need to specify the sampling proviso. These ones, again, as you know, take algebras and data algebras some fixed sampling proviso. Then you need to invert it because you also want this to be yes. Let's say that any generic fiber, any P-complete ring is going to be bounded. But so far, just talk a little bit more about that. We're going to have this kind of nice rings for which I'm going to model theory. Yes, for some.
It will sometimes be one, sometimes.
Let's say for the Rham stack, maybe just this one.
There will be several.
Yes, and for the prismatization, maybe we want to stick with this.
So ring is nice, kind of meta.
Exactly. May vary depending on the theory.
It's also related to the use of word. Is that funny?
Yes. So this state word maybe refers to the word analytic, but not in that sense. Analytic in over sense. In the sense that locally you have a sampling proviso. Basically, data from top of you. Okay. But then this is just the beginning of our picture, basically just what the rings should look like. But still, we want to define whatever the replacements of these delta rings are. And the point is that these delta rings could not be longer rings, could be just some stacks, some spaces here. So we still need to decide what to put there. Maybe we don't want to hold the vectors because the construction is well defined. But similarly as for the Carpenter curve perfectoids, we take this naive construction example. We want, on the other hand, want an analog of maybe bring delta P, maybe more generally just of the whole free stacks. Again, that somehow is going to encode the way our theory is going to be. This certainly we want, because allowing these perfected rings to be here, we want to allow things like Carpenter curves or maybe any for perfect to be in that state. So it turns out that we want of this. Let me say, just denote meaning that morally these are going to be given by a little bit more involved version of part of the curves. Maybe. And we want that given a perfected ring, well, we have the spectrum of anything of these bounded elements of the perfected ring. Usual that. And then we can look, we can remove the locus. Maybe we want just to not to be too strict, but still we want to capture the phenomena zero, characteristic P. And we maybe want to remove some tenure of some certain information. Usually this space is denoted by. Let's say that we not just take if, maybe it's what happens in the different version of the cohomology. Prism is perfect prism down here, these ones. But we localize in this side again because we want to do analytic geometry. So we want to still get space with a certain improviser. And the canonical choice for a certain improviser, both from perfect to space, is not P. It's just the tenure, this second improviser. Again, if you want to see phenomena. This choice is also, let's say, motivated by situations. So indeed, following an idea of Peter about how to try to construct these prismatizations out from, let's say, the already existing prismatization properties. Trying to get these ones. Turns out that it's kind of important to remove this. So we want these ones. This is related with the word analytic. This is related with the word analytic because you have this kind of information. Yes. And also this analytic space. Of course, we also want kind of more fancy versions of this. And this is where this field notion of the curve, maybe this notion of data structure is going to play an important. All right. So say you have that. So now you have the objects that essentially look like a part of the curve. You have the objects that are going to model geometry, which is this nice rings. Then, well, something you would like to have is a contour. Let's say whenever you have a part from the curve, you can just forget whatever kind of structure you get here, and just recall the underlying Analytic space. We're going to have this kind of progressive contour into three stacks. Let me just put it on. Really nice. Right? Similar phenomena. This is just essentially forgetting whatever structure you're putting here, and you just recall the underlying analytic stack structure, the underlying space. In particular, this is what we want in order to get the category of cohomology theory, just taking cohomology of whatever you get into. Yeah, so
this, and
yes.
then is if the notation from this.
This may be the notation for the whole category, not just for the those.
So if
yes, which are content and both. Broadly speaking, because we want this one to be kind of sample.
have you already defined?
No.
It's just a desire.
Exactly. It's just the desired approach. We took.
So
It's
the
fine.
whole, building the storage space.
This category of thought range of groups. Yes. 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 It's open. If you have a construction, you still are given with a Frobenius in this case, because you remove the point that is fixed by Frobenius. And this is not literally Desner structure.
Yeah,
But-
that seems like an element. That doesn't seem like an object because it's desired.
I really want this one to be an object in that way. I still want to be like restricted perfect spaces just to get something like the diagram, whatever. So I still want somehow perfect spaces to be inside there, and the way to get perfect spaces is basically like this. Yes. Except that general object here would be a slightly more complicated general case. So cube is not that complicated, but still it's not bit. The image by people choose a provide like Mark. No. I mean, this one, maybe a bad notation, but basically it's going to be just taking the underlying analytics. From schemes, this paper was strict, but wherever you take a these data stacks, just take the underlying P formal, P complete stacks. You just forget the data structure, and you just look what happened in rings. You can regard via. Yes. Yes. So then, again, once we have this construction, what was left to do is basically define an option of type 1, degree 1, also here. So one advisor, say type 1 to be an object. Again, maybe this one is stack, so this would be again, this one could be the whole stack, so basically just a stack in here. Such that or maybe yeah, let's see, I think I should presentation for this. Are effectively basically deep one of y are the usual length. Degree 1 device just maybe just an element of inf or maybe just an until. Now, because we're dealing with degree 1 devices, these stacks, it means that you can produce a contour in G lower star from these three stacks. Nice. Agree that overall speaking, conflict is evaluated in one of these guys plus divisor. So this is just about one of these guys to this one. And this is going to be a divisor, so this is just going big one of y going to be given by certain kind of degree quantified here, which is just a close, kind of statistic close. Again, this one is a lot of things to actually define concretely, but maybe just the picture to keep in mind is that the strategy to define this analytic prismatization consists on precisely solving each piece of this puzzle. But here, first having whatever the notion of these nice stacks are, that is something that again comes from the theory of analytic geometry. This is the more tricky part, finding this notion of whatever delta rings should be in our situation, and defining what this one is going to be in this case. Once we have that, we'll have again just this picture that essentially this control is what will end up holding these analytic. So in the course of these lectures, we're going to show maybe not just giving this construction of this QP, but also say how things like the crystalline side will be the Rham, the infinitesimal side can also fit in this kind of diagram. So this is not a special platform. It appears many homology theories, but here you just change whatever notion you're going to study by the kind of more geometric version of the state. So again, this is the strategy follow. I think I wanted to maybe do something about the first space time, but I don't know if it's pretty good for the next one. So
It's up to you. Right?
yeah, I think that's good idea. So probably 20 minutes.
Sequence, which can be finite. Definition of the cosine function.
Yes.
However, one can reveal some secrets.
Yes.
Cosine function of field.
Yes. So let me write down.
The note has some similar statements of this shape in this maybe cannot read from if you just know the side.
So maybe let me write down the analog of the cosine of QQ. Prismatization. Some feature that this theory of Franklin curves is going to have that will be important for applications in the timelines is, for example, that you can define and still compute manifold spaces. This category. is turns out that we can compute at least then we just compute two of them that are going to be important to compute.
I think they don't understand the grammatical structure.
So there should be kind of to have some Banach spaces. Similarly, for perfected rings, you can have Banach spaces by taking just global sections of some vector patterns. Something here should also here. So for example, let's say, let's work P, all the spaces. We also remove P equal to 0. And there, we can actually compute two of these Banach spaces. And basically, somehow the prismatization of this for QP is built up such that we get these computations. These computations repeated one of them. But this one, well, in the classical theory of perfect spaces, this is just QP. But again, we want to see some phenomena arising from, let's say, device operators, maybe locally analytic representations. So here we're going to get this locally analytic version QP. Again, like this one is just some kind of visual union of P minus n P A. And each of these guys is going to be like co-represented. Let me just stick. Maybe I actually want to put that on just to mean that it's not just scheme, it's actually of the locally analytic functions of set P. Again, is some kind of stack that was category of comodules. We just specify a stack is related with the category and basically the same as the category of locally analytic states. The other one example, I'm going to do VC of 1. And well, this one, again, the theory of perfect spaces is given by the generic fiber of the universal cover of the p-divisible group of G hat. So basically with something like that. Just some really bold, open, really bold around 1. And we take the limit along the multiplication of P. And this one is generic fiber. So this one is just maybe right here, just 1 plus this and open raised of the residue.
Just illustrate open this center 1,
yes,
and radius 1,
yes,
and 2
exactly.
Then
yes. The thing is that usually in perfect spaces you take these as diamonds and you end up with some perfect point opening this. But here you just want to take it as is. Just this limit. Basically at the level of rings, it's just a whole limit of rings when you rise, when you just take p powers of p. This whole limit of rings. You want to take some kind of decompleted version of this perfect space. And basically the whole theory of this prismatic stuff is to make sense to some kind of decompleted version of perfect with this near perfect. Let me call this maybe just this is just perfect. Yes. Yes. This one is some kind of twisting probability.
Can I ask a question? Sorry about the format of this. So, okay, so as I, my understanding is that a Banach space is some type of a functor from backward.
Yes.
And in your setup, is it correct that so you're studying a generalization of, I mean, you're allowing functors that are not only that you can evaluate not only factoids but on these more general objects.
Yes.
And the equality that the isomorphisms imply are in this sense as
they are already, yes, they are already living in that category. And you also, let's say, can realize it with stacks. These points are with precisely this. These ones already kind of make sense in that category. Oh, carbon thing. These pointers. If you want, maybe technically computing is maybe more like this. This one is maybe a little more.
It's just like so that tilde that sort of analogous to the notion of delta stack and the so it's not so
yes.
that tilde is not only stack Frobenius.
Yes. Has some kind of Frobenius, but the Frobenius has some constraints, some maybe the data structure has some convergence constraints that are kind of known. Like it's not like a condition on the data structure, it's actually the extra structure you put into your spaces. So, maybe modulo proving that any degree one device would look at this trivial or something like that. If one is usually computed as BC of 1 when you remove the zero section, one devices. Then you divide by what would be BC of O star in vertical. Given that doing this in this equation, this one will be, you say that this GM curve isomorphic to a perfect with this under this mapping here. Maybe I should skip this. Then in this setup, this big one is going to be what? Oh, we get this GM curve but we remove the zero section corresponds to the constant 1, 1, 1, 1, 1. So basically we get kind of limit of pointed open unit disks. Then
Sorry. So this is just the objective one. I'm just trying to pass with that side.
Sorry. I mean, again, this was you can make it sense in that category, but maybe just for the same computation, just and then you divide by just the invertible functions in this zero. So you will get this kind of quotient. But this quotient is not appearing from nowhere. You already seen this. QP cross invertibles QP and this local analytic. Then basically what this QP cross is doing, well, I can write it's fine. Basically, the QP cross is just Z cross kind of medians. And essentially what you're doing is just taking a sequence. Is GM cross. Just again sequence of elements from one compatible to two roots. And what you're doing is maybe you have to fix it just to make this grid. Or you're taking it just unique. And acting by some kind of variables, kind of acting by epsilon 3a. And this is this cross, just check. And this p is just rising everything to the p. You look this at the level of coordinates. You have a variable p is this guy, and you're acting on this variable by a. It's a cross, something on p, just like taking a and one. Just the kind of here. You see something wrong. And this p.
Alright, so this choice of a 200
Right.
So it doesn't seem like we use the.
Yeah, sorry, we didn't use this. Sorry, yes, was just question. And this p, on this variable t, you just point to the p. So this is the usual kind of data you get for a figure model. For a figure model, because the power source ring, which in action is simply cross, keeping this by rest of p1, and then t you just act by p. This is exactly the structure you get of this. So again, this deep one is giving you this analytic object, but still in theory of possibility shift is going to be related basically and vector bundles. Cannot be. This result is going to be the same as over-converging figure model. Still, again, this theory can be, things can be reasonably computed. This deep one, also the example of GM, will be very important. Yes. Yes, so this local analytic version, let's say that, is going to have some tangent space. It's going to have some tangent space that is basically the same as the tangent space of the finite, just a one parameter group. And you cannot access to this tangent spaces just using perfect space. These are kind of very just, you don't have any kind of tangent complex. So the reason why this QPLA is going to appear is because it allows your theory to be like slightly more rich than just perfect spaces of just part from the theory. You're still allowing some kind of nilpotent techniques that allow you to somehow still see this like overconvergence, this kind of tangent spaces into objects. Yes. Yes.
What is LA? So have the LA.
Sorry?
So QPLA is equal to union N, it's minus N ZPLA. Can I replace that saying LA?
With analytic. So the thing is that there is not a canonical analytic definition unless you fix some sort of concrete coordinates. Maybe for this one there exists, just given by the say the affine is for this one, such as the data algebra. But again, this one is not like natural in set P as a padding manifold. You're actually remembering a lot the fact that you can embed this one in some database. If you only care this as a padding manifold, which is the canonical thing, you can have to say P. This is the only kind of structure you can get of this. Just the function that locally has some kind of policy. Mm-hmm. Okay. Mm-hmm.
And similarly, you can find
Yes.
Is there a way to
There is a way.
related to basic using only some kind of
There is such a way, but well, I mean, there is such a way, and again, to extend the prismatization to characteristic P, which is something that I just ignored in this example, it's actually important, and we still need to figure out how to define this category using such a kind of word, bit vector, before. But even just in characteristic zero, you can do it using bit vectors, but somehow it's harder than defining just this. It's still, I mean, it's important to get it, maybe to understand some properties of the prismatization, like generically it's going to be this the Rham stack, and there is going to have some touch state point, this kind of features that you will state, at least from this point of view, it's important to maybe compute with these bit vectors. But it turns out that this is how we started using that one. Peter just found that this one in characteristic zero situation has a much simpler definition than just in data. Actually, just using directly what happens in level of stacks. It's much simpler. Much more simpler. But in characteristic P, right now, like the way, I mean, in characteristic P, what you can do is maybe construct a diagonal map, which is directly the prismatization, and maybe not just know how it happens. It means that here I remove, I just took over QP. So these ones are going to live over QP as well.
so
it may not.
But it would be an analytic the way C.
Yes.
But say characteristic P.
It's over FP and double parenthesis T, and maybe some versions of that when you You still have some kind of simple information in some sense. Yes. For example, if you take this Carpenter curve of a vertical space and you go to p equal to 0, you just recover the vertical space which still has some simple information. I mean, I think we have a definition of this less, but I mean, I think we know what we're going to get. Still working out what we get. But actually, very good question, and what we expect that is something very similar to this. This one makes sense. Zero characteristic. Let's say at least for a space like the prismatization, the multiplier of prismatization of a real space in characteristic 0. The geometry is in characteristic 0 and partitions of mixed characteristic. We expect to get something like that, but this one just makes sense. It's just here. This one is again some locally identical versions of this. It's on the formation of this group to characteristic P.
In the yeah. If I like this is supposed to be the foundation.
Maybe yes.
Is that like the round?
Yes. Right. Yes. So you have there. Yes. So maybe it's more to describing this, and maybe this one is maybe the perfect version. Like that. Let me just wait. Okay, so this is perfect visualization. So in this case, one, then we say it's basically just the prismatization to B, which is this GM curve minus 1 divided by this section. Well, you have a point in here which is basically given by some previous units. Once you model by this action, this actually is just a point. Because of any other sequence of periods of unit, change basically is just taking cross. Cross, sorry. So you go outside this epsilon. This is going to be, as you say, this round. So no. Somehow the underline is this one. So in other words, this prismatization is just going to be I don't know. It's associated with Rham star, which again we're going to define later. So basically, you just take this and just shrink along over convergent diagonals. And this one only depends on the diamond attached to QP. So you can write it down slightly more explicitly as again maybe the Carpenter curve attached to CP modeled out like the Galois group of P and take the Rham stack of these things. You just take the Rham. So again, the theory is rich enough to actually relate different versions of this in different ways. This one is question stack like that one.
There you're writing that implementation.
Yes.
And is it possible to write? I mean, like in the usually.
Yes.
Is there like an analog of that?
I mean,
but this is already an analog.
This already, yes. I mean, somehow in characteristic 0, okay, the Rham stack, C is basically just evaluating your stack in reduced strings. So you kill all these deposits. In this case, it's something similar. To evaluate your stack in reduced elements, we are going to be just perfect rings at the end. And then you have this point eta. And in this point eta, you can't just take the closest. It's going to be a divisor here, which is going to be precisely this Hodge state stack. You also can compute that directly, let's say, using this kind. Just kind of adding up. Maybe it's more. Put it down. Oh.
There's a box on it.
Yeah. This point. So basically, Hodge state stack. We can also describe it as well. Basically, we took this root of unit, this one, and we took all possible units. So this is just making QP, where you have add all these roots of units, and well, where you're left going, well, this convenience is doing this nothing, and what you're left doing is just modding out by the Galois group, which is just set across. Nice more. You're doing this locally analytical. This will come out for this presentation because you took the point that corresponds to taking all these sequence of figures, which is going to be the positive point. So the close point that this appears in that place, for this limit of roots of unit is just the cyclotomic extension because you're taking all these limits of roots of unit compatible with like taking powers of it.
Fine, but take the substance of some.
Mhm.
Star gets ring by raising two to S, an element S. See the star gets ring by raising two to S. Then you observe to consider the walls.
It's not that we work with that one. We still work with the after definition of prismatization. And somehow you can think about both descriptions in a similar way. Like the role of these big vectors, maybe the one, degree one and big vector cross, the one you use to prismatization, are replaced by the role of these Banach spaces. Turns out that these Banach spaces, because we're taking, I mean, this example is perfect version of prismatization. Can be computed in more concrete terms in terms of basically things that depends just on the grid parameters. For where this description, let's say, maybe this some better analogy with the cube around prism is like more appealing, more suggestive because of this. This book, I mean, there is a definition just to see this category of harmonic curves. You can compute this Banach spaces. It turns out to be explicitly computed as opposed to using this version of the cube around the prism somehow, which is just it's not something one prism. It is this of the cube. So there's possibly computations here, and this characteristics should something easy. Some sense of computations maybe theoretic form streams. At least this is I don't know. Kind of very discrete, and then it's also clear because the formula in there intrinsically related with classical optics in Calicus theory such as P gamma.
It's a really small question. So is part of the intuition the formula that you wrote? It's sort of analogous to the description of the sort of perfection of the
Yes.
prism.
So I think I should have mentioned that before. The way, let's say, Travis is trying to find this prismatization started by quantitative locus. The works of functions of Juan Esteban Rodriguez and also the work of Rham theory. And then Peter gave a lecture in Bonn last year, where he suggested that actually the object that should depend only on the rigid space constructed conformal schemes should be some perfect version of prismatization. So, or let's say you start with some conformal scheme of C, smooth conformal scheme. Then the perfect completed prismatization let's say relative to the Trapman curve, C, and just C is Well, we can take the prismatization relative to this INF. See? Right? Go back to prismatization to this stack here. Now we can take the realization as an analytic stack. I mean, see, you have a P rings. P complete rings just give you solid rings over INF. And from that, you can just extend this guy to the core category. And now you have a Frobenius actinum here. So the point is that once you pass to this category of analytic rings, you can take this dp by Frobenius, not in P complete rings, where you basically just get the diamond. You can take a Frobenius in a decompleted way. So, for example, if you take the Q-Drum prism and take the Drinfeld Frobenius, you just end up with something that force. Full limit of Q1 or D. And then this update may not just depend on the regenerative fiber, but you take this spectrum of INF and you invert the centromycin. The idea of the by inverting the centromycin, it should be fine. Then the claim is that this claim is only depends generically. So it turns out to be do the computation of this completely, or the complete of this, that actually, again, maybe it's a smooth format scheme, so maybe not crazy because this formula is if you take the generic fiber rigid space, which now you have a smooth rigid space, and you take the prismatization, and maybe that version of prismatization, so let me just put you basically will end up with this limit, and maybe let me just remove it. Maybe you want to do market. So we have this very complicated formula that to check somehow was independent of the generic factor of the ring. But it still was not pleasant because this seems very difficult to compute. And maybe for GM is something you could do by hand, maybe set P, something you could do by hand. But it's not giving the good answer for things like perfect rings. Perfect rings, the prismatization is just naive. You just end up with the fine perfect. And in this setup, the prismatization is not going to be just the perfect Q property space. It will be more complicated. Well, actually more easier. It's just again, genericization the Rham stack and the stack. We have this kind of approximation. Again, by refining and trying to find this category of properties, it's clear that we end up with maybe better descriptions and better definitions of the objects wanted to. This one, at least. This. Yes. Yes. At some point, you want to show that this. Yes. Yeah.
You have already shown. You have shown.
No, it's not. I mean,
you mean not in this talk, but you definitely know that.
We have some ideas what to put there at the same time.
Strictly speaking, it's conjecture.
It's not written, yes. Yes. And like for making this, you actually need to play around with these vectors. Now, because this one is kind of defined in B vectors. You also need to understand this one from the point of view of B vectors. That sense is.